In the previous video, we talked about Kepler's first law of planetary motion. So in this video, we will continue with his second law of planetary motion. And from this law, where we will do some, mathematical problems and some other physics problems related to Kepler's laws of planetary motion. Because the second law and the third law are a bit complicated. Let's start with the definition. The Kepler's second law of planetary motion states that each planet revolves around the sun in such a way that the line joining the planet to the sun sweeps over equal areas in equal interval of time. The best way to understand it is to visualize it, and that's why I have to change my perspective. So in here we have the same setup as the previous video. So suppose we take this as the focus 1 or f1, and I gonna put our sun here or our host star here and take our planet right here. So according to Kepler's second law of planetary motion, the planet revolving around the sun cover of equal areas in equal intervals of time. So suppose our planet move from this point to this point in one day. So let me just put two pawns to give out the points. So these are 2 points, and here we have our planet. We just move from our first white pawn the next to the second pawn, and it took it around one day to complete this much part of its revolution. Now consider this part. Now by just revolving it reaches here, and let's assume that from here to here our planets take also one day to complete this much of its revolution. So I have 2 black pawns here and place it here. So in theory, the area of these 2 sectors will be equal. So these are 2 sectors, suppose this is a near circular orbit. So these are type of 2 sectors. So the area of these 2 parts will be equal according to Kepler's second law of planetary motion. So one thing we should notice, that if it takes same amount of time from moving from this point to this point and this point to this point, then how is it possible to maintain the same speed? No, it is not possible, because here the distance is much more smaller than the distance covered of here. So let me just take out our sun to clarify. This distance is much more smaller than this distance, so we don't need to prove that mathematically because we can visualize it, and that's the base fact. That's why the speed will increase because our distance also increases. So we know that distance is equal to speed multiplied by time. We keep the time constant as 1 day, but the distance varies. So accordingly, the speed will also increase because distance or speeds are directly proportional in the equation. Distance is equal to time, and for that reason the planet revolving around the sun at a further distance will be slower than it is nearer to the sun. So if it covers this much distance in one day, its velocity will be slow from here to here, but when it came closer to the sun, then its velocity will increase because it has to cover a lot more distance in the same amount of time. Now this is Kepler's second law of planetary motion. If you liked the video, like on the like button, and if you liked it too much, consider subscribing because it will really appreciate me. Thanks for watching. Bye bye.